All right. So we are going to continue talking about flip-flops. You guys had your midterm exam the previous class day. I hope you guys did well. I didn't hear many issues about uploading things, so that was really good to see. We are going to try to return your graded work by next Tuesday. So 1 week from today, we'll try to have your grades back to you. Okay, so what is due? What are the announcements today? Homework 8 is due tonight on Gradescope. The next homework will be posted later today. Homework 9, it will be due Tuesday of next week, November 17th. The next studio, which is mainly a simulation studio, which should not take you guys too much time, that's my expectation. Studio 6 is due tomorrow, November 11th. So you guys need to get the check off from the TAs and also the Gradescope submission for that. The next studio, which is sort of an exciting studio, we are going to go back to the FPGA Basis 3 board, Studio 7. That is due December 2nd. So I'm going to give you guys 2 weeks to work on that, and in the middle you will have the Thanksgiving break. But hopefully that is enough time for you guys to work on Studio 7, in which you come up with your own custom message and make it scroll on the 4 7-segment displays. So I will be posting that sometime today or tomorrow, so you guys can get started on that. Daily quiz number 18 is due today on Gradescope, so make sure that you go there and quickly answer the 4 problems. Okay, so this is the announcements. Let's get into the flip-flops. So we have been talking about flip-flops. We have talked about how we design a flip-flop, which is an edge-sensitive device, using 2 level-sensitive devices. So in the previous class, if I go back here, this is what we did. We used a master-slave latch. So there was a master D latch and there was a slave D latch. So it's called a slave because it is responding to the changes of the master, right? And each of these latches is going to be a level-sensitive device. But if I connect them in this master-slave back-to-back configuration and also have the clock, negative level of the clock and the positive level of the clock, control or activate the enable input for each of these latches, then I get a edge-sensitive device. And we proved that by going through the timing diagrams, and we also looked at the analysis of the master-slave D flip-flop. We looked at the first D latch, then we looked at the second D latch using the characteristic table. We went through this in a lot of detail. So it's been a while. If you need to review that, just go back to the previous lecture, the last maybe half an hour or so, and play it on 2x speed to quickly review this at a later time. Okay, let's get into some newer topics now. Other variations of D flip-flops. So right now, what we see in front of us is a negative edge triggered D flip-flop. And the way I know it's a negative edge triggered D flip-flop is because of this bubble right there. So that bubble in the symbol indicates that it is a negative edge triggered. Actually, the edge is denoted by something else. That triangle right there indicates edge sensitive. So both that bubble and the triangle combined indicates that this is a negative edge triggered D flip-flop, which means that the output over here, Q plus, is going to change only when this component sees the negative edge on the clock input right here. So only at these times it is able to change. And what is it going to change to? Well, that depends on what D is at that particular moment. So we know that the characteristic equation of the D latch is, or D flip-flop is, Q plus equals D. So whatever you want the next state to be, just provide that at the D input and also give me the negative edge so that my output can change. So that's as simple as that. All right, so that's your negative edge triggered D flip-flop. Now let's talk about a new input to a flip-flop, which is the enable input, or specifically the clock enable input. And you might wonder, okay, why do we need a clock enable? The reason is this. Clock is usually a crystal oscillator on a particular design. And if it is hardware controlled, you will not be, if it's just hardware, it would be impractical to expect the designer to pull out the clock physically and put it back in whenever they want to switch off the clock and start the clock again, right? So I would want some software control over the clock running and clock not running, which is why I need this clock enable input. And I can include that by having this component right here. So let me highlight this component and ask you guys, what does that look like? Which component have you guys learned? I was hoping that this will snap. Which component does this guy remind you guys of? Exclusive OR? But exclusive OR would have had one more bubble. XNOR. Okay, so here, try to answer this. Over here, if enable is 0, what is, let's call this guy, I don't know, intermediate I. What is I here when enable is 0? Q, right? So I will be Q when enable is 0, because this guy will go through. Sorry, this guy will go through. So Q is right. Let's talk about the other case. When enable is 1, what is I? D. Perfect. So now let me ask you guys, what component does this look like? It's, you see what it is doing. When enable is 0, it is letting one guy go through. When enable is 1, it is letting the other guy go through, right? So in fact, let's do it this way. Let us try to write an equation here. Yes, it is exactly a mux. It's a 2-to-1 mux. So here, let me write an equation at this point. At this point, what is it going to be? D and enable. And over here, the equation will be, the logic equation will be Q and enable complement. And over here, if you see, your new D input is going to equal, your new input to the D latch, D flip-flop is going to equal D and enable, or enable complement and Q. So you see, when enable is 0, it is fed back, right? Q goes back. And when enable is 1, D takes over, the new input. So now what I can do is, I can erase these statements and sketch a 2:1 mux here. And I'm going to try to represent this red box that I drew using that mux. So what is my output? My output is actually just D, because that is driving the D flip-flop. What is my control input? My control input is essentially enable, select input. And when enable is 0, Q goes through, and when enable is 1, D goes through, right? Now let us talk about the difference between the old D and the new D. So what is Q? Q is my previous output. And D is my new output. New input to the flip-flop. And this particular D is connected to D flip-flop. You guys see that? So if you have to make the clock disabled, all you need to do is make enable 0. So if you make enable 0, even though this particular input keeps triggering the positive edge triggered D flip-flop, nothing is going to change because the input over here is not going to change, right? It is going to be feeding it back the same output over here, so that will keep, it will not go, it will not have the ability to change the output. You guys see that? So it's because it's feeding back the same output back into the mux when enable is 0. You guys see that? Now, so that's your, let me point this. This is kind of that. In terms of the characteristic table and the new symbol, that is what we have. So if you make enable 1, only then this design is going to respond to the positive edge of the clock, because the flip-flop that we are using is a positive edge triggered flip-flop. Hold on, guys. All right. So when enable is 1 and this design sees a positive edge of the clock, then your next Q plus will follow D. So 0, 0, 1, 1. And Qn, the complementary form of the output, will be exactly the opposite of Q. However, if enable is 0, meaning clock is disabled, no matter what D is, and no matter if the design sees a positive edge or the negative edge or 0 or 1, no matter what happens, if the clock is disabled, then your Q plus will not change. Q plus will equal Q. Actually, that's what I should include this here. I should include 0, 1, and also the negative edge, right? X, negative edge, last Q. Nothing, like no aspect of the clock can change the next output. Even this should be highlighted in this. And that additional input is included in the symbol using this EN input. So D is your data input. It's a positive edge triggered design. Q is your output of the D flip-flop in true form. Qn is your output of the flip-flop in the complemented form. All right, questions about this? The clock enable functionality that is included such that we don't need to physically remove the clock from the design. We can control it as a running clock, or running clock but not affecting our results, by using this enable input. Okay, so let's now move on to JK flip-flops. So what you see over here is how to design a JK flip-flop using a D flip-flop. So this answers the question here, how to design a JK, a jump kill flip-flop using a D flip-flop. And this slide answers that. But I want to actually prove this result right here. So we are going to do that. Before we do that, let us first agree on the characteristic table of the JK flip-flop. The characteristic table of the JK flip-flop says, I am looking at the positive edge of the clock here, right? So let me highlight the positive edge. I'm looking at a positive edge triggered JK flip-flop. So I'm going to respond to positive edges on the clock input depending on what J and K are. So when J and K are 0, 0, I'm going to be in the memory state. So Q equals last Q. In other words, Q plus equals Q. So that's your memory state or hold state. Next one is going to be, which state is next? You guys tell me what's next. So reset, hold, and then toggle. K is 1, so that is reset. That's perfect. Or kill. Then hold. Reset, set. Oh, okay, set. So set or jump. That's good. And the last one will be toggle. Whatever it was, flips. Last QN, right? Q plus will be Q complement. So that is when the JK flip-flop sees the positive edge of the clock. But if it does not see an edge of the clock, 0 or 1, in fact, you can include the negative edge of the clock as well. So if it is 0 or 1 or negative edge of the clock, no matter what J and K are going to be, Q plus equals Q. So that means that the output will not have the ability to change. It is going nowhere. Q equals last Q. That's it. You cannot change it. It is stored. So we are going to prove this. That's the symbol of the JK flip-flop. JK flip-flop, positive edge triggered JK flip-flop. That's the symbol. And we are going to see how we can design this. Now to design this, we need to start talking about a new kind of table, which is called the excitation table. So let me go here and see whether we can talk about the excitation table. Oh, look, it's sure. So let's add. Yeah. So what I'll do is I'll talk about excitation table. Here. And this is essentially going to answer the question, what should the inputs be, the inputs or excitation be to achieve a particular transition at the output of a flip-flop. You see, characteristic table tells us the opposite, right? So a characteristic table tells us if you have the inputs, what is going to happen to the outputs. But the excitation table is reverse. What should your inputs be in order to get a particular transition at the output? So essentially you are given Q and Q plus, you need to figure out what the inputs of the flip-flop are going to be to get that transition. So let us try to derive an excitation table. And I'm going to try to derive an excitation table for the JK flip-flop. So let's do that. So the inputs now are going to be Q and Q plus. And on the output side of this table, I'm going to write J and K. I'm deriving the excitation table for the JK flip-flop. So between Q and Q plus, how many possibilities should I write for the input side? 4 of them. Brilliant. 0, 0, 0, 1, 1, 0, 1, 1. So your 4 desired transitions at the output could be, it was 0, continues to be 0. It was 1, it was 0, it changes to 1. 1 to 0, 1 to 1, right? So now the question is, what should I give over here in order for that transition to happen? So let's start with simple 0, 0 case. Can you guys tell me, in order to get this particular transition 0 to 0, earlier it was 0, next it needs to be 0. So yeah, in terms of states, you can tell me in terms of states. So hold is 1. What is the other? Reset. Perfect. Let us use kill. All right, sure. Kill. Okay. All right. Let's go down now. 0 to 1. What is next? What do I need to do here to get that transition? Jump is good. Jump or set. What else? Toggle. Beautiful. What about here? 1 to 0. Kill and toggle. Okay, perfect. Kill, reset, toggle. Good. Last one. Hold is good. And set. Beautiful. You guys see that? Now all we need to do is, we need to figure out how to represent these things. How to represent this and this and this and this using J and K as inputs. Let's do that. So what is hold? So for this, let me elaborate this. What is hold? Hold is J is, so J, I will write J here and K here. So both has to be 0 for hold. How about reset or kill? What should be J, what should be K? Zero and 1. Beautiful. Which means for the first entry, I need J to be 0 and K doesn't matter. So I'm going to get my first entry in the table as, for J and K, as 0x. This is for J and K again. You guys see how to get this? Let us continue for the next one. Jump set. Jump is what? 1, 0. Toggle is what? 1, 1. Which means J has to be 1, K is don't care. This is very important, you guys. So please ask questions if you are not able to follow along here. For the third case, kill, toggle. So to kill, I need to do 0, 1. To toggle, I need to do 1, 1. Which means my combined J and K inputs are don't care and a 1. Last one. I can do the same thing again, or I can simply note that 0x, 1x, x1, and the last one should of course be x0. So you can write it like that, or let's do it the right way. Hold is 0 0. Set is 1 0. So it is going to be don't care 0. Questions about how to derive the excitation table of flip-flops. All you need is their characteristic table. If you have the characteristic table, then you can flip it around and try to find what you need to give as excitation, right? What you need to give as excitation, J and K inputs, to get a particular transition to happen at the input, right? That's why it's called excitation table, because you are figuring out the inputs to make something happen at the output. In the characteristic table, it's the other way. Given the inputs, you're trying to figure what happens at the output. All right, you guys, questions about the excitation table. You will use this a lot. All right, so it looks like you guys have no questions about excitation table. Now, if you are comfortable with the excitation table, we are essentially ready to learn how to convert a flip-flop to another flip-flop. Essentially, something like this. How do you design a JK flip-flop using a D flip-flop? Let us try to do that over here. So the question is, the example that I'm going to work you guys through is convert a D flip-flop into a JK flip-flop. So what you're given is a D flip-flop, a data flip-flop. And what you want to design is a JK flip-flop by adding some other logic gates to the design. So there are a few steps that we are going to walk through to get that conversion, right? So given D, desired JK. Let me highlight that. This is given and this is desired. Now, the first step is going to be to write the next state table or the characteristic table of the desired flip-flop. What do you desire? JK flip-flop. So I've started using the JK flip-flop character next state table. So I've written J, K, previous output Q, and the current output Q plus. I've just left it as a blank for us to fill it out. So can you guys tell me what Q plus is going to be for the first column? So let's say the first two rows. Zero and one, right? Because it is in the store state. So actually, let's do this. Different color. So you've got store here. You've got kill here. You've got jump here. And you've got toggle here. That will make it easy to fill it out. So when you store, output doesn't change. 0 remains as 0, 1 remains as 1. For the next two, we are in kill. Output is going to be 0 0. Absolutely right, Ian. Next one, we are in set. What are you going to say for Q plus? 1 and 1. Beautiful. And the last one, we are in toggle. So it was 0 and 1, it will flip to 1 and 0. Perfect. That completes our first step, to write the next state table of the desired flip-flop, JK in this case. Next, we are going to write the excitation table of the given flip-flop. So the excitation table of the given flip-flop is quite easy to write for the data flip-flop. I'll show you how. So if you wanted the transition from Q to Q plus, right? So you see Q here, Q plus here, previous output, current output. Again, 4 possibilities, 0, 0, 0, 1, 1 to a 0, 1 to a 1. What should I give over here in order for those transitions to happen? Right? That's the answer to excitation table of D flip-flop. So let us try to go through this. It's going to be very simple. What should I write here for the first entry? What should D be? 0. Perfect. What about the next one? It's a data flip-flop. Whatever goes in comes out, right? So in fact, the characteristic equation of the D flip-flop was Q plus equals D, right? So we could literally just write that, right? Like just these two, the same. And we are done. So whatever you want at the output, you just provide that at the input and you activate the clock input. That's it. And it'll happen. So that's your excitation table for the D flip-flop. We are done with step number 2. Step number 3 is to write both those things. So on the left, we see the next state table of the JK flip-flop from step number 1. And now we are going to combine step number 2 alongside it. Oh, I missed a plus here. So from earlier, I had figured out Q plus, the next state table. So let me copy that. I had figured this out, so I'm going to paste it over here. And hopefully it aligns well. All right. So that was step 1. Maybe this will help if I can box this up as step. Sure. Now step 2 is going to be kind of an overlap. So step 2 is going to be from here to here. Right there. I just need to figure out what to give at D in order for this Q to change to Q plus. Essentially, refer back to the excitation table from step 2 and fill in the column for D, right? So it was pretty simple. Q plus was equal to D here. So I don't need to refer to the excitation table too many times. I can simply write out Q plus equals D here, right? So I can simply say, all right, Q plus, 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 done. Now, because I am given a D flip-flop and I desire a JK flip-flop, I need to figure out what to provide as an input to the D flip-flop. That's the given flip-flop in terms of J and K. So what I'm going to do is I'm going to consider these particular columns. Let me check them. J, K, and Q, right? What are the inputs J and K and the previous output Q? How is that related to the D input? So for that, I'm going to use a K-map because I have a 3 variable case here. My inputs are J, K, and Q, those 3 things. And I'm going to fill this out to write an equation in D for D in terms of J, K, and Q. Because I'm given D, I need to figure out the JK because that's what I desire. So let me just take this column here for D and transition that to a K-map. 0, 1, 0, 0. I'm reading the last column here. 0, 1, 0, 0. 0, 1, 0, 0. 1, 1, 1, 0. Hopefully you guys agree with that. Next, simplest. That should do it, and that should do it. So if I now write the simplest equation here for D, what is that going to be? I have J is 1 and K changes, Q is 0. Or what is next? K complement and Q. You guys see that? Now, let us try to take this and relate to that. That was our result, right? Let us see if this diagram represents what we derived. What was given? D flip-flop was given. So that is exactly what is given here. That's why we are designing the desired flip-flop using the D flip-flops. So that's what gets sketched first. Now let's try to write the equations here. What equation do you have here? J and Q complement. And what is the equation here? K complement and Q. And this guy is what D is. And if you notice, that matches that exactly. So what we did here is we designed, by the way, is this a positive edge triggered JK flip-flop or is this a negative edge triggered JK flip-flop? Positive edge triggered, yes. So it is a positive edge triggered flip-flop because the given D flip-flop was responding to positive edges, and that's exactly what our clock input is for the overall JK. So it is going to be a positive edge triggered JK flip-flop designed using a positive edge triggered D flip-flop. Quick question. What if I wanted to design a negative edge triggered JK flip-flop using a positive edge triggered D flip-flop? What would I do? Negate the clock. Perfect. I'm done. Oh no. So you see, we don't need to worry about flip-flops having hazards because the changes that happen are already limited by setup time and hold time, and there is propagation delay. So the timing constraints are already set in place. We don't need to worry about hazards on top of that. Make it into a NOR gate instead of a OR gate. No. So if you just negate the clock, we are done, right? So now, instead of responding to the positive edges of this CLK input, it is going to respond to the negative edges because you have flipped it, right? So by simply adding the NOT gate here, you get that done. All right, questions about this design. How we converted from a given D flip-flop to a JK flip-flop. There is no secret in this. This is kind of a very important topic. You absolutely should expect a problem on flip-flop conversions on the final exam. All right, so let's do something different here. Let us try to deal with toggle flip-flops. Can you go back step 3 for a second? Yeah. Right here. No problem. All right, so now let us talk about a toggle flip-flop. A toggle flip-flop is very helpful in counters. You know why it is helpful in counters? Very simple. The least significant bit of a counter will toggle every count. The next most significant bit of a counter will toggle every second count, every fourth count, every eighth count. So things that are in a counter always keep toggling. So a toggle flip-flop becomes very helpful in the design of counters. And you will see that when we try to design counters using flip-flops. So let's talk about T latch. What is the characteristic table of a toggle latch? Like the D latch, it is just one input, T, one output, or sorry, two outputs, Q and Qn. But I'm representing over here the current state, Q plus. And my previous state was Q. So when T is 0, don't toggle, meaning Q plus equals Q. Don't toggle. Other words, store it. When T is 1, please toggle. Q complement. Or flip. Note over here, my Q is previous state and my Q plus is my current state. Now, can we expand this compact characteristic table into something that is including the possibilities of the previous outputs? You see, when T is 0, my previous state Q could have been a 0, could have been a 1. In the same way, when T is 1, my previous state Q could have been a 0, could have been a 1. So now I'm expanding this compact characteristic table into something that evaluates Q plus for every possibility of previous state Q. So you have 0, 0, 0, 1, 1, 0, 1, 1. In the first two columns, first two rows, you don't toggle. So Q plus equals Q. And it is over here. And in the next two columns, we toggle. So 0, 1 becomes 1, 0. Now let us try to write the characteristic equation of the toggle flip-flop. What is a characteristic equation? The characteristic equation is a relationship between Q plus and Q and the inputs to the latch. So inputs to the latch are T, the outputs are Q and Q plus. So can you write an expression of Q plus in terms of T and Q here based on this table? Perfect. T exclusive or Q. Why is the thickness of my pen not good? In other words, it is going to be T and Q complement or T complement and Q. So this is your characteristic equation of toggle flip-flop or toggle latch. The difference is toggle flip-flops respond to the level of the clock. Toggle latches, toggle flip-flops. Flip-flops respond to edges. Latches respond to levels. That's the only difference. All right, questions about the, T latch, at least, their characteristic table. How did we derive the characteristic equation over here? And why do they play a good amount of, so why do they play a crucial role in the design of counters? We actually did this a little bit ago, characteristic equation of D. Let us just do this again, just as a quick review. When D is 0 and 1, what is your Q plus? Can you guys walk me through this? 0 and 1. Perfect. Q plus equals D, right? Next, over here, we have both the possibilities of Q here, 0 and 1. So Q plus, again, what is it going to be? D. 0, 0, 1, 1. So what is the characteristic equation of D latch or D flip-flop? Q plus equals D. There's nothing, nothing exciting happening there. Next, let us try to derive the excitation table of a T flip-flop. And you guys need to help me with this. This is excitation table, and this is for the toggle flip-flop. So 0 to 0, what should I enter at the top? All you need, okay, so 0, 1, 1, 0. All right, that's a perfect answer. So if you're having, an easier way of thinking about this is, don't toggle, 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 don't toggle, right? So 0, 1, 1, 0. So that's your excitation table of T flip-flop. Excitation table of JK flip-flop, actually we had derived it a little bit ago. So we don't need to do that again. It was just here. So let me just copy this and paste it over there. We don't need to do it again. All right, let's do this now. Design a toggle flip-flop using a data flip-flop. What are we going to start with? We are going to start with the desired flip-flop, right? So what is desired? Toggle flip-flop. That is why we are starting with the next state table of the toggle flip-flop. What should I write for T, Q? Well, these are going to be my inputs. T refers to the input to the T. Q refers to the previous state, previous output. So in terms of zeros and ones, I will have 4 possibilities. Now, what is Q plus going to be? Again, you look at whether it is toggling or whether it is not toggling. So for the first 2, we don't toggle. For the next 2, we toggle. You guys see that? 0, 1, toggle. All right. So that's step 1, essentially. Step 1, we have finished for this problem. We have completed writing the next state table for the desired flip-flop, which is toggle flip-flop in this case. Next, step 2 is what? Step 2 is write D using the excitation table of the given flip-flop. We need to figure out what we need to give. We need to provide as an excitation to the given flip-flop to achieve toggle functionality. So we need to figure out what the last column is going to be. So what should I enter at the last column? Same as Q plus. Perfect. Okay, so we are done with step 2. Step 3 is essentially combining both in order to write an equation for D in terms of T and Q. So if you wanted to write an equation for D in terms of toggle and previous state, what would you write? which operation is happening here. So 0 0 it is 0, 0 1 it is 1, 0 1 0 it is 1, 1 1 it is 0. In other words, when T and Q are the same, D is 0. When T and Q are different, it is 1. Exclusive OR, perfect. And Preston is also right. T exclusive OR Q, which is also TQ complement or T complement Q. Let us try to build it here. So I already have a positive edge trigger D flip-flop drawn. I'm going to sketch my exclusive OR gate, which is going to drive my D input. And somewhere over here, I have a toggle input here, which is essentially going into my exclusive OR gate. The other input of exclusive OR gate is Q. So what I'm going to do is go back here, go top. And I also need to add my clock input so that this guy can function. And that is it. We have designed a T flip-flop using a D flip-flop. Both are positive edge triggered. Again, if you need a negative edge triggered, you just add a inverter to we negate the clock and done. All right, questions about this example? Okay, now let us do something very interesting here. Let us try to design an absolutely new kind of flip-flop using any flip-flop that we have learned. So I need a volunteer who can pick some random sort of things for this. Who wants to volunteer? So essentially I need someone who can randomly pick states. Who's going to be the volunteer? The more random, the better. No. So guys, listen. Here, so do you guys want, what do you guys want to do here? Like 0 0. Let's first look at the volunteer here. So Ajit went first. I will start with his. We will try to design an AP flip-flop using what flip-flop would you like to use to design this? You have data flip-flop, toggle flip-flop, D flip-flop. That is easy. JK, let's do JK. Let's do JK. Because D is a little bit too easy. All right, so we are designing an AP flip-flop using a JK flip-flop, right? So what I want you guys to, what I want to randomly ask is, when A is 0 and P is 0, which is what happens in the first two. Oh, AP is the Ajit Parmar flip-flop. So it's based on the student's name. All right, so when A and P are 0 0, you have 4 options: store, set, reset, toggle. what would you like to happen? Someone can be random toggle. All right. So if toggle is for the first one, then I need to do q plus is going to be 1 and 0 here. All right. What's next? 0 and 1. When a is 0, p is 1, what do you guys want to happen? Again toggle. All right. This 1 and 0. All right. A is 1, p is 0. All right, kill. That is reset. All right, 0, 0. All right, what is the last one? 1 and 1. What do you guys want to happen? What are you guys so fond of toggle? Store, yes, thank you. All right, so we have some storing, right? Otherwise, it was going to be useless. Toggle. All right. All right, so we are doing some storing. We are not just setting here, so which is kind of okay. All right. So we have come up with an arbitrary next state table of the imagined AP flip-flop. And we are going to implement this using a JK flip-flop. So let me write JK over here. And toggle, yes. Now, to do this, I'm going to need my excitation table here of JK. Otherwise, it is going to be a lot of back and forth. So I'm going to copy that, paste it over here, minimize it, and write the inputs that I need to provide for J and K to get that change from 0 to 1 or 1 to 0 and so on. So I'm looking at these two to figure out these two, these two to figure out these two, and so on. So 0 to 1, 1x, 1 to 0, x1, 0 to 1, again 1x, 1 to 0, again x1, 0 to 0, it is 0x, 0 to 1, 0 to 0, 0x, 1 to 0, 1 to 0 is x1, 0 to 0 is 0x, 1 to 1 is x0. All right. So I've used my excitation table of JK, and I've written the inputs to the JK flip-flop that I need to provide here. The next step, K-maps. Let me actually do this. I can erase this now. I will do the first K-map for J, and the next one will be for K. So let's see. The inputs are going to be A, P, Q, A, P, Q. The first one is for J, second one is for K. Let us build up the skeleton. 0, 0, 0, 1, 1, 0. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. All right. For J, it is going 1x, 1x. 0x, 0x. All right. What is the simplest equation for J, you guys? A complement is right. Next, for K, x1, x1. x1, x0. You see, this is what happens. All right, there's a little bit of change there. All right, simplest expression for k. Group of 4 there. Group of 4 there. Oh, there is one more. No, it made it a little bit more interesting. All right, so k equals a complement, or what is the other one? P complement. Sure. Okay, so it's not going to be so exciting, you guys. As you see these. All right. So anyway, what did we have? We had JK flip flop. So if you have a JK flip flop, I'm going to start drawing with the JK flip flop. So are we working with a positive edge triggered or negative edge triggered? Negative edge triggered. Okay, so we are working with a negative edge triggered JK flip flop. Okay, we of course have Q and Q complement over here, and we have J and K. That's my given flip-flop. Now once I figure out what is given, I sketch it out. Now I go back to my equations. J is a complement, K is a complement or P complement. So I have, say, A over here. That's going to drive J. I'm done with that. Next, K is A complement or P complement. A, P, we are done. A and P. Yeah, you can do A and P as well. Sure. That'll work. Either one will work. Next, what do we have? Clock. What do we do about the clock? See, the reason why this is not so interesting is because we didn't use feedback on the overall thing. That would have been even nicer. That was because you guys were so fond of toggling everything. So let's do the clock. We are doing clock. Oh my gosh. All right, we don't get anything. We just, all right. Are we doing a negative edge triggered AP flip flop or positive edge triggered? All right. We are done with the design. So this is a negative edge triggered AP flip flop using a negative edge triggered JK flip flop. Can you design a negative edge triggered using a positive edge triggered? Absolutely, yes. All you need to do is add a NOT gate to the clock. That's it. You can absolutely do that, yes. We should call this a toggle flip-flop. All right. Now, people who are going to be watching this asynchronously are going to be confused. So you guys, people who are watching asynchronously, we were having fun with storing and toggling. That's why we called our AP flip-flop, which was based on a student's initials, to a toggle flip-flop. Those names are just like arbitrarily chosen. But what you need to focus on is the design process, the stepwise, going from the next state table of the desired flip-flop to actually designing the desired flip-flop using a particular given flip-flop. So, just to note over here, in one of the exam stoggers, in one of the exams, I had given the characteristic table of two arbitrarily chosen flip-flops, MN, XY. And I designed one flip-flop using the other. So that meant that you had to kind of derive the excitation table of one of the flip-flops, which was absolutely new, didn't belong to the JKD toggle family, like a known flip-flop. We could do a lot of interesting conversions with this. All right, questions about this process of how we dealt with this? I had a little bit of fun doing this. I hope you guys did too. Now, let us talk about the T flip-flops a little bit more. Now, in this, we are going to use the clock enable input just as we did earlier. So you see the T flip-flop symbol typically is this. Let me show you here. Add a page after. So a T flip-flop symbol would be a box, a T input right there, clock input right there, Q and Q complement. So this is, for the positive edge trigger T flip-flop. So that is a typical symbol for the T flip-flop. However, what you can do is you can include another input enable, and you can actually treat the T input as the clock input. So we don't have clock here, we just have enable and we have T instead of T and clock. And it is going to function exactly the same way as the traditional T flip-flop, this guy. Let us see this. The first question you would ask is, when is the flip-flop enabled? So I'm going to highlight those times where the flip-flop is enabled, meaning EN is 1. Those I've highlighted in blue. Now, when is the output going to change? Well, the output Q is going to change when there is a positive edge on the signal that you connect over here, right? So when is that positive edge? So let us highlight even that, maybe in green. Positive edge on T input, positive edge on T input, positive edge on T input, positive edge on T input. Once you highlight those, all you would focus on is Q. Is it going to toggle or is it not going to toggle? So let us start so assume that Q is 0 initially, you would have to make that assumption. And then if it is starting at 0, it toggles over here, right? Because you have the positive edge of the clock and it is enabled, so it's going to change here. At this time, there is a positive edge of the clock. However, the flip-flop is disabled, so it is not going to change. It is going to continue to be a 1 there. Next one, toggle input, you have a positive edge on the toggle input and it is enabled, so it's going to flip again and it is going to flip again over here. So essentially something that is similar to this, right? There are two different ways of thinking about a T flip-flop. This guy goes here and you have enable now. You guys see that? So traditionally you will see T and clock, but you could also switch this around to clock enable and T input on the clock input, and it will function exactly the same way. Now, if you expand this a little bit more, exactly the same way as we designed a T flip-flop using a D flip-flop, if I go back here, you see what we had? An exclusive OR gate. So here we were doing a design of T flip-flop using a D. So we used a D to get a T, and we simply had an exclusive OR gate. That's all we had. And if you did that with this new sort of flip-flop with enable and T input, enable is now functioning as T. So enable exclusive OR Q is going into D, and my T input is going to drive the clock input. So this will also function like a positive edge triggered T flip-flop with the clock enable using the D flip-flop. But the process is exactly the same as what we had before when we were converting a D flip-flop to a T flip-flop. And again, over here, this is going to be repetitive. This is very simple. J and K, right? So if I make this guy 0 here, enable 0 here, then my JK flip-flop will be in the store state, right? Because J and K will be 0, 0. What the clock does in this circuit? Oh, we don't have a particular clock in this circuit. We simply are using a toggle input, so something like a switch to make it flip. Instead of connecting that to a clock input, we are calling that clock as a toggle input. So we are just referring to this input as T, because if T is 0, don't do anything. If T is 1, don't do anything. But when T goes from 0 to 1, that's when you change. So it just periodically switches Q. Yes. Depending on what EN is. Only when EN is 1, it will flip. Let's come to this. Over here, enable is 0, then J and K inputs are going to be 0, 0, which means Q plus will be Q. No going anywhere. It is stored. But when EN is 1, what will happen? If EN is 1, we are going to be in the toggle state. So when we are in the toggle state, Q is going to be, Q plus is going to equal Q complement only when there is a positive edge on T. So when there is a positive edge on T, Q plus will equal Q complement, otherwise it will store. That statement is indicative of a T flip-flop that we have designed using a JK flip-flop. And even if you did the whole entire process of converting a JK flip-flop into a T flip-flop, that would boil down to this. Just connect both the inputs together. All right. Let's do something else. In the 4 minutes that we have, let us try to sketch the output here. So what you are given is a T flip-flop. It's a negative edge triggered T flip-flop. You are given the T waveform, you are given the clock waveform. These are timing waveforms. And let us say you are asked to sketch the timing waveform for Q. What would you do here? Assume starts at 0, right? So if you assume that Q starts at 0, you would have to assume that. If you assume that Q starts at 0, the only times that you need to worry about are negative edge of the clock input. Does Q toggle at the second negative edge of the clock? In the previous diagram? In this guy? Were you referring to this one or the new example? Oh, let us see. I don't know. So it's a negative edge triggered design. So all I need to highlight are the negative edges of the clock, right? So if I highlight the negative edge of the clock here, I'm going to say, all right, those are the only instances when Q can change. So if I assume that Q starts at 0, it is going to stay at 0 until that time. A straight line would have been even better. And at that time, what is going to happen? There's a negative edge on the clock. However, T is 0, meaning don't toggle. So when you don't toggle, you continue to be a 0. All right, until next time. Over here, you are absolutely right, Roland. Now, you see, there is a negative edge on the clock and your toggle input is 1, which means toggle. So you will toggle just after that, right? So I'm going to, just after that, it will toggle until next time. Over here, T is 0. Don't toggle. So it will continue to be that. Right. So this is an example of how you can sketch the waveform, the output waveform for Q, assuming that it starts at a 0 for a given T and clock inputs. Questions about this example? We have kind of assumed here that our rise time is 0, fall time is 0. We have kind of ignored the setup and hold times as well. So assuming that all those are not playing a role, we are just simply tracking the functionality of the T flip-flop. Let's do another example here. There's a T flip-flop connected in a certain configuration. You're taking the output of the T flip-flop and feeding it back to the input using an inverter. And you have been given the clock signal. It's a square wave. Again, it is a negative edge trigger design. So all you would have to do is, focus on the negative edges of the clock. The positive edges are not going to matter. The levels are not going to matter. So now what do we do? Let us try to assume that our output is a 0, right? So if our output is a 0 here, let me write it in red. If our output starts off at a 0, right here, 0. What is going to be over here? There is going to be a 1 there, and that 1 comes back and there is a 1 here. You guys see that? So when it sees, so from here until here, it is going to stay at 0. But at the next negative edge, we have a T input, which is 1 because of this. So what is going to happen? It's going to toggle, right? So it's going to toggle here from 0 to a 1. And then stay there for some more time. Let us see what happens. Now, when it is 1, you see what happened? This guy will go. Now this guy is changed. This guy is changed to 1, which means this guy is changed to 0, which means feeding it back, this guy is changed to 0. If that is the case, we are not going to toggle now. Don't toggle. What happens here? It'll not toggle. That's it. That's all it can do. It'll continue to be at 1 there. How do we know how fast the signals are switching? We would have to know. We would have to be explicitly told that. Like if it was a real component, we could look up typical minimum maximum timing. Otherwise, we need to explicitly mention that. Also, wouldn't it toggle on the third edge? You see, it won't, right? Because once Q becomes a 1, right? Once Q becomes a 1, this will always be at a 0 and this will always be at a 0, which means you will always be in the don't toggle state. After you reach Q equals 1. So after you make the output 1, it is going to get stuck there. It's never going to go down. All right. Now, a few more things that are attached to this lecture, particular lecture slides, but these are slides that we have completely gone over. We have talked about this in the previous this lecture and the previous lecture. So this is just a place to summarize the characteristic equation. These we have derived these earlier. This was when we were talking about the SR latch, the characteristic equation of D, the characteristic equation of JK, and the characteristic equation of T flip-flop. We have derived these, 3 of them today, 1 of them in the previous class. So think about this as like a summary slide. This is a summary slide for the next state tables. Again, we have looked at them not all in one place, but this slide brings everything into one place. SR, JK, data, and toggle. All the flip-flops, their current states and the next states, depending on their inputs. So a summary of next state tables can be very useful as a crib sheet for your exams or a reference sheet. The next one is the excitation tables. So these are excitation tables for SR, JK, T, and D. We actually derived it for JK, T, and D, but if you apply the same sort of scheme for SR, you could also derive this. Again, there is excitation tables and the characteristic equations. So these are just summary slides that are at the end. Okay, so this completes the conversation about flip-flops. Now in the next lecture, we are going to start building registers using flip-flops. So this theme of building bigger and more interesting components using smaller and simpler sequential elements will continue. So we did latches. Using latches, we designed flip-flops. Now using flip-flops, we'll design registers, and then we'll go on to designing counters. So I will see you guys with the design of registers in the next lecture on Friday. All right, I'm going to stop recording here.